This is lecture 24 of Data Science 100 and Data Science 200, and the topic is big data. So this lecture is really, I think, the culmination of everything that we've looked at in this class put to practice. And so in this class, we started by looking at how companies and organizations store their data. They store their data in databases. And those databases are often relational database management system-based systems. They access that data using SQL, the structured query language. Well, in this lecture, we're going to look at big data. We'll look at what is big data, a lot of examples of big data, and we'll look at analytics that we might want to do with big data. We'll also look at data warehouses and data lakes, where organizations store their big data. We'll look at distributed data storage and processing, and the challenges that are associated with it. And we'll look at platforms for working with big data, like Apache Spark and Modin. Okay, so let's zoom all the way out. Big data is really about actionable analytics. We take all of the data that we collect from our databases, from all different sorts of multimedia and other content, from logs of systems, and we perform an extract, transform, and load step to get that data into our data warehouse. And from that data warehouse, we generate data products. You can think of these as reports. We also generate business intelligence, what's going on. We also generate analytics that action can be taken based on. Now, data warehouses, those have been replaced by data lakes. So this is really, think about it as the 200,000 foot view of what we're going to go through in the first half of this class. Okay, so let's start with what is big data? Well, big data is data of sizes beyond the ability of traditional software tools to quickly capture, curate, manage, and process. It can be unstructured or semi-structured or structured data, but most oftentimes it's going to be unstructured data. It's data that requires parallel or distributed computing tools to process. It's too big for one machine. So another way we could look at what is big data is this plot. So you can think of data as having three different axes. There's the volume of data. Well, big data, we're talking about terabytes, petabytes, exabytes of data. There's the velocity. So traditionally we might have thought about small data as, data that we work with on a batch or a periodic process. But with big data, we may have data streaming in that we're processing in real time. There's also the variety of the data. We have tables and databases, which we already looked at in this class, but there's also rich multimedia data like photos and audio and web. And there's social data and video data and mobile data, all of which is unstructured. So there's just three axes that we could think of for data. Now, what do we want to do with our data? We want to use big data for actionable analytics. There's no point to collecting data if we're not going to use it. And so there are three different types of analytics that you can think of doing with big data. The first is descriptive. Tell me what's happening now. Looking at the big data, tell me what's happening now. The second is predictive. So what will happen in the future? And then the third is prescriptive. So given the data in front of me, what should I do about it? Okay, so let's look at where we get big data from. Well, it's everywhere. All around us, there is big data. It's everything that's happening online. It's user-generated content from web and mobile applications. It's open data sources. It's the Internet of Things and machine-to-machine communication. It's scientific computing. So for each of these 5 areas, let's go through and look at some of the big data that we get from those areas. So, it's everything that happens online. We could record every click you make, every ad impression every ad that's shown to you, that's an ad impression, every billing event, every time you hit fast forward or pause in Netflix or Hulu, every server request, every transaction, every network message, every fault, and so on. Now I say we could, but companies actually do. So Facebook records all of the metadata about what you're doing when you use their applications, when you're scrolling through things, when you're clicking on things, when you're responding to somebody. And that's over 60 terabytes of data that's generated every day. Now, what do they do with it? Well, they use it to drive ad revenue. So which ads do they show you? Because they want to show you ads that you'll actually click on. Another source of big data is user-generated content. That's you and me. When we use the web, when we use mobile applications, when we're using Facebook or Instagram or Google or Yelp or TripAdvisor, or Twitter, and so many other applications, we're providing the big data. And so if you look at all the data that's being generated on the web, Google's index of that is over 10 petabytes and growing fast. Another source of big data is health and scientific computing. So we can see here on the far left, things like the Large Hadron Collider, which is generating 25 petabytes of data when it runs. We can see tweets, we can see World of Warcraft servers, the US Library of Congress, and so on. In the center is data being generated by the Protein Data Bank. So that's a place where people index proteins found in living organisms. And you can see that data is growing exponentially. On the graph on the far right is the cost of sequencing a human being. And you can see it's dropping faster than the cost of Moore's Law. It's less than $1,000 now to sequence a human being, to learn all of the bases that make up their DNA. And there are projects like the 1,000 Genomes Project, which sequenced over 1,000 individuals and has generated over 200 terabytes of big data. There's also graph data. So lots of interesting data that you'll look at has a graph-like structure. Whether you're looking at social networks or telecommunication networks, computer networks, road networks, collaborations, relationships, they all have a graph-like structure. And some of these graphs can be big data. So think about like the Facebook user graph. When you have billions of users, that's a lot of nodes and a lot of edges. Machines generate data. So when you run a web server, every time a client connects to that web server, that connection gets recorded. When it occurred, what was requested, what the status was of that request, how much data was returned, all of that is recorded. That becomes big data when you have a lot of web servers. Every machine also has a system log where it records the various activities that are happening on that machine. Again, across tens of thousands of machines, that's big data. And then there's open data sources. So there are a lot of open government and other data sources. There's the US's data.gov and healthdata.gov, which provide an incredible array of data that's generated by the federal government or collected by the federal government. There's the CIA World Factbook and the EU Open Data Portal. And now many cities and states are offering their own open data portals. So we saw earlier in this class, the city of Berkeley's police data portal. We used that for one of the classes and also for one of the demonstrations. There's also a huge list of public data sets. So this link that's here on the slides, I encourage you to go take a look at it. Many of these data sets are free and open, and you can download them and you can play with them and you can combine them with other data sets to see what insights you can discover. And so a lot of times with my students, when they're trying to solve a problem and they need some data, I say, oh, go look at one of these data sets. There might be an interesting one that would be perfect for the algorithm that they're trying to develop and test. Okay, so those are the sources of big data. How do we use it? Well, it's also ubiquitous, the usage of big data. And so I just want to go through a few examples of how people use big data in the real world. So the first one I'm going to start with is aerospace. And when you look at a plane, so someone described a 747 as 1 million parts flying in close formation. And that's true of any major airplane. It's a lot of moving parts all flying together. And today, they're all networked and interconnected, and there are tons of sensors. So just an A GE jet engine records 5,000 data points every second. A Boeing 787 generates approximately half a terabyte of data for every flight. And an Airbus A380, that has over 25,000 sensors. So what do you do with all of the data flowing in from these sensors? Well, you can do things like optimize fleet maintenance operations. So plan maintenance. So that engine collecting all of that data, you can build a model of when things are failing on the engine or about to fail. Look for the signals like a rise in oil temperature or a fluctuation in the fan speed and so on. And so you can use that to plan when you do maintenance, to position spare parts, and to anticipate when a component is going to fail. The other thing you can do is to improve the operational performance across flights or across the fleet. So you can look at a city pair, two sets of cities, and look at how pilots fly the plane from one city to the other. Now, there are many different ways you can fly the plane. You can crank the throttle up and fly that plane a lot faster, but it's going to burn a lot more fuel. And it may actually be more efficient to throttle back a little bit and use less fuel. Same thing when you take off. Rolling back the throttles after you take off, doing that quickly, ensures that you burn less fuel. And so you can look at how individual pilots fly the plane relative to all their other peers and use that to optimize, well, maybe these pilots need to be retrained in how to better optimize the use of fuel. You can also use it for things like, measuring how the landings are. Hard landings, very bad for planes. They tend to stress the components. And so you can use that to identify when there might be fatigue occurring of parts because the pilot is landing the plane very hard. And again, feed that back into training. Okay, so another use for for big data is autonomous vehicles. So here's a picture of how we collect data for an autonomous vehicle fleet. So we have all of our vehicles. They're collecting data from LiDAR sensors, from radar sensors, from tons of cameras, and vehicle sensors that are measuring engine performance, wheel angles, and braking, and stuff like that. Throttle position sensors. We collect all of that data in a data center. There's a data lake there. We're going to talk about those more in just a moment. Some of that data we save off to cold storage because it's a lot of data. And other data we use to train the models that control how the vehicle operates, the autonomous vehicle. I'll get to that in just a moment. So, typical vehicle generates between 1.4 and 19 terabytes of data per hour. 19 terabytes per hour of operation. So that translates into anywhere from 300 terabytes to over 2 petabytes of data per car per year. And you end up with about 1 billion images. Of those images, you'll take more than 3 million of those images and have them be labeled by humans. So this is a picture of a crosswalk. This is a stop sign. This is a traffic light and it's yellow. This is a pedestrian. This is a bicyclist, a motorcyclist, and so on. So when we look at a company like Waymo, each of their vehicles collects between 11 and 152 terabytes of data per day. Their fleet collects between 2.2 and 30.4 petabytes of data every single day. Now, all of that data that's being collected, we take some of that data and we use that for training, to train our next model. And then we test that model by running it in a simulator where we can see how it will react to scenarios that have been recorded or generated synthetically. And based on how it reacts, whether it reacts well or poorly, we go back and we might train another model if it has a few too many accidents, right? And then eventually we get models that we're happy with. We deploy those models out to the fleet. Training those models, those deep neural networks, takes over 800 GPUs for each test car that you have in your fleet. Here's another example of big data usage, and that's smart homes. And so in a smart home, you can put a thermostat, like a Nest thermostat, and it controls the heating, ventilation, and cooling system and does machine learning at scale. The goals here are reduce your energy consumption while increasing the comfort of the people in the house. And you can do that by monitoring the activity, you can monitor the usage, you can look at location patterns. What's the temperature outside today? What's it predicted as the high and the low? When do I predict the occupants will be in the house? If they're not in the house, I don't need to heat or cool the house. But if I can predict when they're going to return to the house, I can pre-cool or preheat the house so that the house is at a good temperature when they arrive. So we can do lots and lots of analytics. And again, falling into those three categories, we can do descriptive analytics like what's happening now. Predictive, what will happen, and prescriptive, what should I do about it? So if I predict it's going to be cold today, then the prescriptive action is to turn on the heat. Or the descriptive action is to look, is the heat heating the house? Is the house getting warmer? And so we can actually use these analytics to build thermal models across many different homes and types of homes. And so the really impressive thing here is you just put this thermostat on the wall and it figures out the model of your house, how it reacts to the heating and cooling system being turned on as a function of the solar load on the house from sun, the thermal load from heat or cold outside. And it can see when the house stops behaving normally. So for example, if it tells the furnace to turn on and heat, and the house doesn't start heating, then maybe something's wrong, like a filter is clogged. If that's not treated, it'll lead to the furnace shutting off. It could lead to damage to the furnace or to the blower. And so you can give alerts and early warning of things going wrong in the house. Similarly, if you detect the fire alarm going off or the carbon monoxide detector going off, you can shut off the heating system. Okay, another example of how we can use big data is for e-commerce. So here we do predictive analytics. We analyze millions to billions of transactions. And Alibaba just announced a 3-year smart garment factory that they've been building. Now, that's really important in China because garments account for $328 billion annual market. And 1 in 4 garments is shipped via an Alibaba platform. So what they're trying to do in the smart garment factory is yield an overall 75% reduction in the production lead times. So from someone has a concept for a new piece of clothing to when that piece of clothing actually shipping out the door and ending up in consumer hands. So one of the things they've done is build what they call AI fabrics. So these are fabrics where a designer on the computer screen can simulate what happens if I dye it blue, or I dye it green, or I dye it red. And they can immediately see what that fabric would look like under different lighting conditions, and then put that fabric onto an actual simulation of a human and see what a piece of clothing would look like. This is in contrast to before, where what they'd have to do is they'd have to get samples of fabric, they'd have to dye it, they'd then have to have someone cut that fabric and produce the garment, and then put the garment under lights, take pictures, and then they could finally see what it looks like. In addition, the factory has AI-powered cutting machines and network sewing machines. So they can track a garment from the raw fabric coming in all the way to when it's going out the door to a customer. Here's another example. And it's a little bit of a mixed bag. So again, for e-commerce, we can do predictive analytics by analyzing millions and billions of transactions. So Target did this. So Target said, hey, let's figure out how we can market to women in their second trimester. Because it turns out that is a peak buying time. That's when women start to buy items for their new baby. And what they figured out is if you can get those people to come into the store and start that buying during that time, they'll keep coming back, buying more and more and more. And so you'll get a repeat customer. Okay. So how do they actually do this? Well, every customer of Target has a guest ID. That guest ID value is linked to the Target data that they have, and it's also linked to third-party data. So they buy data on households and demographics and zip codes and all sorts of available data about individuals. Now, what they discovered by looking at all of their purchase data was that women started buying larger quantities of unscented lotions and cotton balls and other items at the start of their second trimester. So they built algorithms that learned what were the factors, what were the items that women would purchase right before they delivered their baby. And so then, how do you get people to come in the store? You send them coupons. And so they sent diaper coupons to the account owner of a teenage girl who had been shopping at Target. And when he got that, he was not happy because his daughter wasn't pregnant. So he went down to the Target store, demanded to see the manager, and said, "Why are you sending my daughter, these coupons?" And they said, "We have no idea. We know nothing about why you're getting those coupons." He then went home, had a conversation with his daughter, and discovered that she had just discovered that she was pregnant. So it's not clear that this is a good use of predictive analytics, but it is pretty amazing that predictive analytics were able to figure out that the daughter was pregnant before she knew she was pregnant, and just simply by looking at her buying habits. So that's an example of what we can do with big data. Okay, another example is precision medicine. So NYU, New York University, built a COVID-19 severity score model. So the way they did this was they collected data from 160 hospitalized patients in Wuhan, China. They then used machine learning to identify 4 significantly elevated biomarkers in the patients who died. And that's versus those who recovered. So then they built a model using these biomarkers as well as other factors that are known to be predictive for severe cases of COVID-19, including age and gender. So then they validated this model using patients in New York City. So collecting data from those patients in New York City hospitals, they were able to validate that their model actually was predictive of how severe someone's disease would be. Now, why do you do this in the first place? Well, the goal here is to give providers data to help them make more informed care decisions that lead to better outcomes for patients. One of the challenges with this disease is that hospitals can very quickly be overwhelmed with patients, and then they have to decide how much care to give each one of those patients. Well, if they could know which patients were going to be mild cases or less severe cases, they could devote less resources to those patients and reserve those resources for the patients that they know are going to be much more severe and life-threatening cases of COVID-19. So another example is genomics. So human genome sequencing will generate over 40 exabytes of data per year by 2025. We'll be able to sequence lots of people because the cost is dropping. Now, how big is 40 exabytes? Well, for perspective, YouTube estimates that by the year 2025, their video uploads will be about 2 exabytes per year. This is more than a factor of 20 larger, or a factor of 20 larger, roughly. So what can we do with genomics? We can do research to better understand diseases, the causes of genetic diseases, the severity of the disease, and how that disease might progress in an individual. We can use it for interventional techniques. So earlier, better treatment of diseases. Identifying hazardous mutations at birth means we can do early treatment, or identifying them early in youth, we can start treatment earlier. That leads to better outcomes. And from a clinical standpoint, being able to rapidly identify infectious pathogens. Another aspect is for research into agriculture. So completely different from humans, but directly affecting humans because we know we're going to need over 50% more food to feed 9 billion people by 2050. That's World Health Organization estimate. At the same time, climate change is going to reduce the yields of our crops by 25% or more. So by using genomics, we can engineer better agriculture to be able to feed those people, even in the context of a hotter or more extreme temperature planet. Okay, so let's switch gears and look at how we use data in organizations. And so there's lots of buzzword bingo here. You're going to see lots of these terms thrown around in companies. So the way we'd like to think of our data in an organization is we have a database. It has inventory information. I can query that database. But the reality, very different. Our data is likely scattered across many different databases. We may have a sales database for Asia that contains sales in yen. We have our inventory database, and then we have another sales database for our US sales that's in dollars. So we might have a European sales database that's in euros, and so on. And then we have an advertising database that has data on our marketing and advertising campaigns. So we have these operational data stores, and they really capture the now. What are the current sales? What is our current inventory and stock? And these are in many different databases scattered across an organization. They're absolutely mission critical. So we have to be very careful with these operational databases because they're serving the live, ongoing business operational needs. They're managing inventory. They're powering e-commerce and point of sale, right? If the point of sale database goes down, then all sales in all of our stores stop, right? If our e-commerce database goes down on Cyber Monday, we lose one of the biggest sales days of the years. So these are mission critical databases. We want to be very careful with the access, who has access to these databases, the workloads that get run against those databases, and so on. They may have very different formats, right? So the sales database has data in yen for Asia and data in dollars for US and data in euros for Europe. They may have different schemas, right? Some of these databases may be from companies we've acquired. So we're a multinational company with many different subsidiaries, and they're all going to have different databases with different schemas. And live systems, they operate in the now. They don't worry about history. Because for a point of sale, I don't really care about history. I care about this current sale. What's the price of this item now? So what we really want as you know, to be able to work with this from a business analytics standpoint is we want a consolidated, clean, historical snapshot of the data. That's not an operational data store. That is a data warehouse. So a data warehouse collects and organizes historical data from multiple sources. So from each one of these databases, we're going to do an extract, transform, and load periodically into the data warehouse. So this is data that's extracted from the remote sources, transformed into a standardized schema, and is loaded into what's usually a relational SQL database. Not always, but oftentimes will be a relational SQL database. Okay, so what does that mean? We go extract, transform, and load. So first thing, extract and load, they give us a snapshot of the operational data, right? So it's a historical snapshot. It's all of the data living in a single system when we finish, right? And it allows us to isolate our analytics queries. Maybe we're doing deep learning. Maybe we're like Target and we're trying to figure out, how do we predict when a person's going to go and start shopping in our stores. We want to separate that from our business critical services, from processing those user purchase transactions, right? And so this is easy, right? Well, a lot of things could go wrong, right? We don't want to accidentally drop some data. We may have to deal with the fact that input formats change. This happens, and it happens a lot. And so that's really the role of the transformation step, right? And so the transformation step is going to clean the data and prepare the data for analytics in a unified representation. And so you've done ETL multiple times in this class. We give you a data set and you have to clean it up before you can actually go and work with it. And so the challenge here, this is difficult, as you know, right? It often requires us to use specialized code and tools. And it's oftentimes, transformation is a brittle process, right? The input data format changes and it breaks, right? And, something goes offline and we don't get the extract from that data. And so then we don't do the transform. And yet we load something in. So this whole process can be very complicated, right? There's different schemas, there's different encodings, there's different granularities, and there are a lot of things that can break. So ETL code it's kind of the one thing you really don't want to have to be given the task of, because maintaining it, creating it and maintaining it can be particularly challenging. But it's critical to our creation of our data warehouse.